So, have you ever wondered what the big deal is with quantum computers? What makes them so incredibly powerful? Well, it all really boils down to one key difference from the phones and laptops we use every single day. Today, we're going to break down the classical bit versus the quantum qubit to see how this one tiny change could literally redefine the future of computation.
First up, we'll use a pretty simple maze analogy just to get our heads around the basic idea. Then, we're going to zoom right in on the core building blocks. Yep, the bit and the qubit, and see how their differences lead to these just mind-bending leaps in power. After that, we'll compare the hardware side by side, and then wrap it all up. Sound good? Let's go.
Okay, to really grasp the difference here, let's start with a simple but super powerful analogy. Just imagine you're trying to find your way out of a massive, incredibly complex maze. Now, a classical computer, it's like a person who has to walk down every single path one by one, right? They go down a path, hit a dead end, have to turn all the way back, and then try the next one. It's a very slow, very linear, step-by-step process until they, finally stumble upon the way out.
But a quantum computer, whoa, it is a completely different beast. Imagine it's not a person, but a mist that just seeps into the maze. It explores every single path, every nook and cranny, simultaneously. It doesn't have to choose a path. It basically exists in all of them at once, finding the exit almost instantly.
So how on earth do they do that? Exploring all paths at once? Well, it all comes down to the fundamental unit of information each one of these computers uses.
Okay, so on the left, we've got the classical bit, the simple, reliable foundation of all our current technology. And on the right, the much stranger quantum bit, or qubit. The core difference between them is really certainty. A bit state is definite, it's one thing or the other. A qubit state, well, it's all about probability. Let's break that down a bit more.
The classical bit is just like a light switch. It can only be on, which we call a 1, or it can be off, which we call a 0. There is absolutely no middle ground, no dimmer switch. It's a simple binary choice. That's it.
But a qubit operates in a completely different way. It can be a 0, it can be a 1, or, and this is the part that bends your brain, it can be a combination of both at the exact same time. Think of it like this sphere. A classical bit can only be at the North Pole, R0, or the South Pole, R1. A qubit can exist at any point on that entire surface.
This totally unique capability has a name, and you've probably heard it: superposition. It's the principle that allows a qubit to exist in multiple states at once, and it is the secret sauce behind a quantum computer's immense power.
So why is this whole idea of superposition such a game changer? Well, it's because it completely rewrites the rules for processing power and for speed. Let's just see what happens when we start putting a few of these qubits together.
Okay, let's start with just one qubit. Because of superposition, it can hold the values of 0 and 1 at the same time. So right off the bat, one qubit holds two possible states.
Now watch what happens when we add a second qubit. We don't just get one more state, we double our capacity. Two qubits can hold four possible states all at once: 0, 0, 0, 1, 1, 0, and 1, 1. And if we add a third qubit, you guessed it, we double it again. We jump from 4 states straight to 8. You can see this incredible pattern here. Every single time we add one qubit, the processing power doubles. That, my friends, is exponential growth.
This graph shows the result perfectly. Just look at it. Notice that blue line representing classical memory? It's a steady, straight, linear increase. Now look at that orange curve for quantum memory. It's not a line, it's an explosive exponential leap. With just a handful of qubits, you can handle an amount of information that would be totally impossible for even the biggest classical supercomputer.
Of course, this radical difference in how they work requires a completely different kind of physical hardware. You can't just build these things out of the same old parts. So let's take a look at what these machines are actually made of. As you'd probably expect, these two different approaches require completely different guts. Conventional computers are built from things we're familiar with, like CMOS transistors and a central processing unit, or CPU. Quantum computers, on the other hand, rely on some seriously exotic hardware, like squids and a quantum processing unit, the QPU.
So in the classical world, the CPU is the brain, right? It uses its arithmetic and logic unit to do all the math, and it's all built on billions of these tiny little CMOS transistors that act as those simple on or off switches we talked about.
But in the quantum world, the brain is the QPU. And what's fascinating here is that the logic unit isn't some separate part. The entire network of interconnected qubits is the logic unit. And these incredibly delicate connections are often managed by super-sensitive devices known as squids.
Okay, we have covered a ton of ground, so let's bring it all together into a single, consolidated view for a really clear side-by-side comparison.
This table pretty much brings everything together in one spot. We've seen the basic unit difference, the bit versus the qubit in superposition. We know they're governed by totally different laws of physics, and all of this leads to that exponential speed difference. But here's the critical trade-off, and you can see it right there in that last row: error sensitivity. For all their amazing power, quantum systems are extremely fragile and super sensitive to any kind of disruption, while classical systems are incredibly robust and reliable.
Now, if you ever need to recall this, say for an exam or you just want a simple way to remember it, this slide is perfect for you. For the bit, just draw a line with a switch at either 0 or 1. Simple. For the qubit, draw a sphere, label the poles 0 and 1, and then just draw an arrow pointing anywhere inside. That arrow right there, that represents superposition. It's a fantastic little mental shortcut.
All right, let's do a quick final recap of the most important points, and then I'm going to leave you with a question to chew on.
So the crucial points to take away are these. A classical bit is a simple binary switch. A qubit uses superposition to be in multiple states at once, and this is what allows a QPU to get those exponential speedups. This also means quantum memory scales incredibly fast. But, and this is a big but, all this power comes at a cost. Quantum systems are very, very fragile and sensitive to errors, while our classical computers are stable and super reliable.
And that brings us to a final question based on that exact trade-off. We know quantum computers are exponentially faster, but they're also extremely fragile. So why would an organization that needs absolute rock-solid reliability like the military still depend on slower, classical computers for critical day-to-day administrative work? What do you think? Let us know.